Analysis and design of footbridge connecting, second floors, of Block A and Block B of MIET, Jammu. Abstract footbridge is a bridge designed for pedestrian traffic which are used to let people cross the road safely without disturbing the traffic below. There was a need to join the two blocks of MIET College, Jammu so as to access the passage in rain and other climatic effects and also to increase the aesthetics of the campus. A footbridge is designed to connect the two corridors of the two blocks. This project mainly consists of the detailed design of such a footbridge by considering manual and software approach. Survey of the site is done both by QGIS software and manually by Theodolite, plotted using AutoCAD. The design and analysis of footbridge is done using STAAD.pro Connect Edition. Keywords: footbridge, pedestrian bridge, STAAD.pro, finite element analysis. 1 Introduction 1.1 Types. A footbridge, also a pedestrian bridge, pedestrian overpass, or pedestrian overcrossing, is a bridge designed solely for pedestrians. While the primary meaning for a bridge is a structure which links two points at a height above the ground, a footbridge can also be a lower structure, such as a boardwalk, that enables pedestrians to cross wet, fragile, or marshy land. Bridges range from stepping stones, possibly the earliest man-made structure, to bridge water to elaborate steel structures. Another early bridge would have been simply a fallen tree. In some cases a footbridge can be both functional and a beautiful work of art. There was a need to join the two blocks of MIET College, Jammu so as to access the passage in rain and other climatic effects and also to increase the aesthetics of the campus. A footbridge is designed to connect the two corridors of the two blocks. This project mainly consists of the detailed design of such a footbridge by considering manual and software approach. This project mainly consists of the detailed design of such a footbridge by considering manual and software approach. Survey of the site is done both by QGIS software and manually by Theodolite, plotted using AutoCAD. The design and analysis of footbridge is done using STAAD.pro Connect Edition. From model generation, analysis, and design to visualization and result verification, STAAD.pro is the professional's choice for steel, concrete, timber, aluminum, and cold-formed steel design of low and high-rise buildings, culverts, petrochemical plants, tunnels, bridges, piles and much more. To perform an accurate analysis, a structural engineer must determine such information: structural loads, geometry, support conditions, and materials properties. The results of such an analysis typically include support reactions, stresses and displacements. This information is then compared to criteria that indicate the conditions of failure. Advanced structural analysis may examine dynamic response, stability, and nonlinear behavior. Technology domain. The proposed solution, i.e. footbridges, as per modern trends in civil engineering. It falls under the domain of design of structures. The approach used is analytical by considering manual and software approach. Different types of design footbridges include timber footbridges, steel footbridges, concrete footbridge. Footbridges can also be built in the same ways as road or rail bridges, particularly suspension bridges and beam bridges. Some former road bridges have had their traffic diverted to alternative crossings and have become pedestrian bridges. Examples in the UK include the Iron Bridge at Ironbridge, Shropshire, the Old Bridge at Pontypridd and Windsor Bridge at Windsor, Berkshire. Most footbridges are equipped with guardrails to reduce the risk of pedestrians falling. Various footbridges. 1. Tilak Nagar Station in Mumbai. 2. A pedestrian overcross in Nanjing Road, Shanghai. 3. A footbridge to an Orthodox church in Greece. 4. The Chain of Rocks Bridge near St. Louis, Missouri. 5. The Corktown Footbridge in Ottawa. 6. The Davenport Sky Bridge in Davenport, Iowa. 7. The Dunlop Bridge at the Circuit de la Sarthe, Le Mans, Sarthe, France. 8. The Esplanade Riel in Winnipeg, Manitoba. 9. The Gateshead Millennium Bridge, London, England. 10. The Goodwill Bridge at Brisbane, Australia. 11. The Ha'penny Bridge in Dublin, Ireland. 12. The Hungerford Bridge and Golden Jubilee Bridges, London, England. 13. The Jade Belt Bridge in the Summer Palace in Beijing. 2. Methodology 2.1. Survey. It was done using Theodolite and was then plotted using AutoCAD. From the drafted plan, the calculated span equals 30 m, scanmap.jpg. Final.png. 2.2 Specifications of footbridge. 2.3 Load calculations. 2.4 View of the STAAD.pro user interface. 2.5 3D view of the footbridge, STAAD.pro modal. 2.6 Earthquake loading. 2.7 Section properties after designing. 2.8 Total dead load after designing. 2.9 Steel design results from STAAD.pro. 1. Span equals 30 meter. 2. Clear walking width between main girders equals 2 meter. 3. Clear height of bridge equals 1.8 m. 4. Type of truss configuration equals Pratt truss. 5. Plate thickness equals 0.02 meter at bottom and 0.01 meter at top. 6. All members are of mild steel, angles and plates. 7. Site location equals J and K, earthquake zone V. As per is 800:2007 clause no 2.2.4.1. Unit mass of steel, P equals 7850 kg/. Modulus of elasticity, E equals 2.0x. N/. 1 dead loading as per is 875 part 1. 2 live loading equals, no dot of persons, 150, times 75 kilograms times 9.81, 30 times 1, equals 3.67 kN/m2 4.0 kN/m2. 3 earthquake loading as per is 1893:2016. Then the model was designed in AutoCAD and was then imported to STAAD.pro Connect Edition, where after applying the materials, dimensions, loading conditions etc. analysis was run and various calculations obtained from STAAD.pro was interpreted and any beam failure was redesigned until we got a stable structure. The following is the final details and specifications. Shown in X and X direction, similarly are in other directions. 3 conclusions. 1. The whole study was done on STAAD.pro and the structure comes out to be stable as per guidelines. 2. STAAD.pro provides an extremely flexible modeling environment, broad spectra of design codes, and covers all aspects of structural engineering. 3. Designing in STAAD.pro is lot quicker and more accurate. All the diagrams like shear force diagram, bending moment diagram etc. can be easily obtained and real-time visualization of the behavior of structure can also be animated. 4. All the loading conditions like seismic loads, wind loads, dead and live loads can easily be taken into account as per Indian standards. 5. Moreover, this computer simulation technique provides us a stability check criteria for members and sections. 6. We can have a clear vision of the estimation of materials to be used. 7. This simulation study provides us an ease of determining stress contours, by which we can easily predict premature failure and yielding limit of sections. 4. Conflict of interest. On behalf of all authors, the corresponding author states that there is no conflict of interest.